Like we're good. See how what the latency is on this. Okay. The hell YouTube didn't really get through. Okay. Hopefully we can keep up with what's going on. So we're going to stream today. Sorry for the hiatus. Life gets busy. But today we're going to talk about color space conversion. Hi Carlos. Still did not see the YouTube one come through. Interesting. There it is. Wonder why it's not coming on the screen chat. The chat box. Really have options, do it? Should be coming through. Oh, Carlos, I saw your chat. Don't worry about it. So today we're going to look at color space conversion, which I dealt with when I did like the video filters with pink, and I wanted to put it on the OpenFPGA environment or ecosystem so people could kind of do whatever custom color space they wanted to do on their device. They could tweak it dynamically by the by a very small floating point value or fixed point value in this situation. Okay. So we're going to talk about color space conversion. So this is from the Pink repository. They have their own color space conversion, basically doing the same thing. And in their situation, their video, their HDMI ports on the Pink device were blue, green, red, and not RGB. And normally when you're working on colors, you're normally expecting RGB, or you have to convert back and forth. And OpenCV does it really well, but it's also very easy to do that matrix manipulation inside the FPGA. So in this situation, they have 3 pixels coming in, and they could be RGB or BGR or some other type of format, and then you're going to have these coefficients, and basically you just take this input value times this coefficient and add these values to the output value. So you have the 3 coefficients per output value and then 3 bias values per output value. Here's an example of a conversion where you're taking in 3 and it's becoming out 1, and in 2 is out 2, and in 1 is out 3. And basically converting from BGR to RGB. It's kind of a basic one. If we look at they're implementing this in HLS. I'm going to try to do a Verilog example. Hopefully it goes well. I'm going to do a Verilog example without using any DSPs. Do some simple fixed point. We'll see how it goes. But basically, yeah, they're just taking the input value times the coefficients, adding them together, and outputting them. And they're using this stream format in the Xilinx ecosystem. We're focusing on Intel FPGA, so this is kind of pointless. But it's simple logic. We can look at some example coefficient matrices they have. This is BGR, so this is a 1-to-1 matrix right here. Right? 1, 1, 1, 1. They have the coefficients at the very end. This a little bit. Then they have the RGB where they're converting it. And then they have the YCBCR values, which are a little bit more complex. And then they have a simple grayscale where they're just taking, doesn't look like a grayscale. It looks like they are just applying the red color to everything. That is a bad grayscale. I disapprove of that grayscale. That is a lazy grayscale. Much better ways to do a grayscale than that. So, let's talk a little bit more about more complex color spaces. So these are some simple video formats and whatnot, but when we deal with like pictures and the RGB values of our screen, let's go to the Wikipedia, right? The Wikipedia had a good, like that image right there is what I want to look at. So there's different RGB values, and there's like, what does your screen support? What does your print display support? What color? Stuff like that. So there's very different areas where your RGB can go. And so there's conversion tables. It's really hard to find these tables, so I'm not sure how easy it is to get these. But so these are the coefficients. They don't have any biases, and these are just straight RGB or 3 color space conversion. So these are a bunch of different values. And so I wrote up a quick Python example that takes a simple RGB bar, and we kind of explore RGB to, so if we go back here, there's like RGB to Adobe. So this first one where it's like the 5.7 right here, I created this matrix. I guess this is the bias values there. I didn't really manipulate this very well. So we have these bias values, and then we apply these. I kind of just did it by hand. I could have probably done proper matrix things, but I just typed it by and capped it out. And then we have this. So this is taking the raw RGB colors and going to the Adobe color set, and then going to, well, that one's Adobe, right? Yeah. And then we're going to SRBG for this other one. And it's kind of like they're darker in this situation because we're just taking it away from the color. We're not really doing anything necessarily useful because just the screens aren't really meant to show this very well. But here we'll give tools for people to manipulate it themselves. So what we're going to do next is focus on a test bench. So we're in EDA Playgrounds. Can I close this sidebar? Can I? That's fine. And we have, probably zoom in, shouldn't I? We'll just put this in tab then. Okay, zooming in. That should be mostly legible. Okay, so we're going to create a very simple system Verilog test bench and a Verilog dot. In this situation, are designed under test. We're going to, so we'll start with the module that we're testing real quick. We have the clock, red, the red input, the fixed coefficient, and the new red value. Right now we're just starting at 0. It's empty, but we're going to then throw this into our test bench, do clock, red, and apply those inputs into the module. And then we're going to, what's the word I'm thinking of? Stimulate. We're going to stimulate the module under test, and we're going to assign some values. We're going to go through a few clock cycles. Then we're going to test for that value and see if it passes or fails. This is the VCD dumps out our waveform, and this is just like a little helper function to see. So we run this. We'll see down here. It decides. Are you not letting me run this? Right when I needed a video, you're not letting me run this? Do I just keep hitting run? Do I need to do it? I'm gonna pick a different tool. A synopsis. Yeah, I'm gonna get upset if we can't just run this. It's running. Tested it beforehand. Okay, let me use. Okay, do I have another run somewhere? Don't have anything over there. Okay. Okay. This is it. We happy now? Okay. Try reopening it. Give it a name. Why do we not have a name? OpenFPGA. I guess we'll just call it color space. Save. Maybe this just does not work well with streaming. I'll have to remember that. Yeah, it's being really slow. Well, I guess we'll just let this run. Why we got? I'm gonna look at Verilog for loop. I want to do for loop. Okay, looks like we're just going to do a very basic for loop. I can do it. Okay. Bonus maximum 60 seconds. Why? Okay, finally. Cool. Okay. So, about 90 nanoseconds in, we test the value and it failed. So now what we're going to do is, really, you can't copy that. Okay, so we want to be able to go and slowly take our fixed coefficient, which is going to be one value above the 0.8 values below the point. So we're going to do different stages. And let's see. So first we'll start with an always block at the pause edge of clock. Sorry, my syntax says we're just going to begin and end. End. And a very simple way to do this is what we're going to do a 9-stage system. So we're going to do a reg. Going to be 0 to 8 stages, and it's going to be a 8 down to 0 value. I think that's textbook. See if I have an example somewhere of a large array. Okay, the Verilog memory array. Okay, so we have to put it after it. Yeah. I am not up to date with my Verilog. Stages 0 to 8. And yeah, we're just gonna do now. How do we pick the value? Okay. Um, so we're gonna say if fixed coefficient, the eighth bit is 1, begin, and else. And we're just going to do a simple like stage 0 going to equal red or stage 0 going to equal 0. And at the end, we're just going to assign I think I can just do see if it's happy with that. So line 24. We need square brackets. I'm living too much in oh, didn't save it. Whatever. We can retype stuff. Great. Reg 8 0 stage 0 8. And we're gonna say stage 0 play clock. And we're gonna say if fixed coefficient it's 8 1 again else and stage 0 is going to equal red. Okay, cool. We saved it. Let me run it. Okay, you do not like the I am not use. The Verilog check 8-bit. Why can't I remember how to get a single bit? I know how to do it in VHDL just fine. Sub array. How do you? Yeah, you just say switch 17, which that. Okay. Is it the if statement that you're not happy about? That'd be the if statement. Weak. near else. Um, uh, oh, the begin is if it's multi-line. If it's single line, we don't need that. Okay, I'm remembering Verilog. I should remember Verilog more often. Okay, cool. So we'll assign that, and it's happy because the test finished. But what we want to do, something but like that. So that would make this half the value. Basically like that. Page 8. Okay. The best way to do this. We're going to do a for loop. So I can't copy that. But basically it's normal syntax. The I come from anywhere. We need an integer I. So yeah, they just have an integer I listed. Integer I guess. For I equals 1. I is less than 7. Do 8, I guess. Equation. I equals I plus 1. Again. And what we're going to say is if that value of fixed coefficient right here. So we're going to take this. But we're going to put I here. It's going to slowly go up. And we're going to say stage. This has to be 7. Stage of I plus 1 is going to equal stage I plus Verilog concat. Verilog concat. We're going to do zeros. Do we need to do zeros? We just might be able to add the things of different sizes because I'm evil that way. We could just might be able to do so basically we're shifting down red. The red is getting smaller. So it's basically going to be red of 7. I mean, it's just going to be what? Red shift over by I. Verilog shift operator. Can we just do it? Shift right logical filled with 0. Yeah. We want to shift right. Yeah, we want to shift right logical. So we're just going to do something like that. And we should be done. signals that what's has to pass. Can I not look at do I need to go deeper? Um the file get module errors. Why? How do we I don't know. How do I let's see, EDA Playground BCD file get module. Guess we could try that. Oh, we're starting. Okay, sorry, my bad. We need to start from stage 0 and go to that. That should give us looking for. And we want to be able to dig down. Dig down. Guess we could just I guess we could just add it as an output. Right, we can just have these as outputs and read them. Who really cares? We should just, I guess. There you go. Doesn't like. Oh, is it because I am not doing that? Blocking, non-blocking. I need to get used to it. First clock cycle, we have something happen. I'm doing my loop wrong. Again. I could unroll it. I'd rather not, but I guess for now we'll just roll it real quick. The stage. So on the for loop to work. Okay, see, that's what I'm expecting. So let us figure out. So I think it might just be because our logic's bad here. So what we want to do is we want to do 7 minus I and 0, 1, 0, red. I 7 minus 0, 1 plus 0, 0, 0. Okay. Like I would like this a lot better with Vera later. Okay. Oh yeah. That's what I expect. Why is it not shifting down the rest of the way? Is it just not synthesizing that? Maybe it's not synthesizing it because we're not actually using it. But okay, so radix. Okay. So it is happy with that. But if we go back here, we want to make this be stage 8. Oh, we didn't do it else. That's important. That's important. stage else. We do nothing. Okay. I can do this. Eh. I ship very well. But oh well. Still comes out clean. So we have a lot of coefficients and a lot of other things, so it's gonna be, I guess, difficult. We'll just do I guess we do a single pixel and then maybe I'll figure out the rest later. Um we didn't really talk about I don't really think the rounding up of the coefficients. We didn't really work on that. That's another issue with the whole 9-bit of high and low. We didn't assign it to a new value, right? We have to, anyways, we gotta save the red. We have to save the coefficients the entire time. Okay, yeah. Now I see. Well, let's just see if we can get this to work another value. Right, so if we say um or there, we should see, let's say 1 4, and we should get a 1 4 out. Coefficient is 1 4. And we got 8. No, new red doesn't get assigned something until the 85 cycle where it's an 8. We have the 10. We have the 20. Yeah, we didn't get added together. Well, we should we do this, we should get a 10 out. Yeah, we get a 10 out. What I expect. And if I do an 8 here, I should get 18 out. Shifted the 1 over and we added it. So is that not working? Adding the value, changing the red. I may want to change all those to 7. Okay. 4 did come out. I am really confused to what's happening. So what we're going to do is we're going to make all these actually 7-bit. I have pointless for it to be 8-bit at the moment. If we do this, we should be able to see the numbers better. Weird. We're saying line 19 of design. There. That should work out better. Hmm. Okay. Okay. So 0, 0, 4. That's what I'm expecting. So if we put a 1 here, turn to 14. Weird. Oh, did it? It shifted by 2. Did it not? Do I need to like that? Weird. Okay, so there's the right state value being added, but that was 8. Why? It should just add something new every single time, being close to 2x the original number. The arithmetic weird? And it is. Hmm. Okay, now we should see a walking. So stage 0 is 10. We should see a walking 1 with this. I want to see if I can figure out why this is slowly decreasing value. Okay, so we have unhappy, but let's go see what the values are. 1, 8, 4, 2, 1. Okay, so the shifting is working. Is it the add? This 16 plus 8 should be 1, 6. So it definitely shifted correctly. But why is it not adding correctly? Is it okay, unsigned arithmetic add in there. So there should be unsigned. Maybe we just do +1. Yeah, we're just gonna add a 1 to it. But that it decreased faster. Why was the is it just turning that into a shift value? Oh, it looks like it's shifting extra value. So what you want me to do? Just like the that doesn't make constants. Do verilog add. Why they're just adding things? Okay, is it just that? Now if we add the previous shift, we're just collecting that into the shift value. That's weird. I'm confused. I think the shift is all powerful. You can't trust. Ah, there we go. That's what I wanted. Yeah, the shift is all powerful. You can't trust it. I'm already tired. I'm not sure how much longer we can go today. I need to figure out how to get more energy. Okay. I'm gonna have to think about this. But we got a basic like little arithmetic thing here. And what we need to do is we need to store this red value and it needs to carry with the stages. The fixed coefficient needs to be saved and carried with the stages. So in the end, we're going to need a lot of registers to fully pipeline this. We're going to need like basically um, we're doing 8 down to 0. I'm not sure about that. Save. Oh, wait. We're gonna need 9 stages at I think, and we're gonna need 12 of them. Stage it, and then our inputs need um, 0. Save what's going to need to go 0 to 8, and we're gonna have to do 0 to 2. Are you happy with that? Are you gonna give me a bug for trying to do all that? No, it's okay with that. So what we need to do outside of so I'm gonna say saved inputs stage 0, stage 0 is gonna equal red. And then here we're gonna say save inputs equal I 0 equals +1. It's going to be this +1. We'll pipeline it down the stream. And then we're going to want the saved input. It's going to be that. Okay. And now for the we're going to do the same thing for the coefficients. 0, 0 equals going to be our single fixed code. Basically, we're going to do the same line here. Oh, these need to be none. There we go. So we want to see, and then we're going to do save coefficient at value. Now we should be able to pipeline values. I'll show you in a second if the builds will pipeline some values. Okay. Now the cool thing is we now can assign a new one of these at the end of like each clock cycle. To figure out some different values. But we can do 0, 8. Be half of 8, which would give us 40. 22 here. We'll ask for that's 1.25 to that. Basically just ends up being 24 in the end, I think. 3 AA 055 and FF 002. Okay. So now we kind of fully pipeline this. Hopefully. See how it goes. Back to our waveform. Okay. So our first answer is 14. 14, yeah. Next is multiply these basically, which is going to divide that hat. It's going to be 40. Boom. This one we're basically timesing by 1 point. It's going to be 1/16, 1/1/16, which would be 24-ish right here. Then we have 33. We're dividing that by a quarter. Just C, which kind of makes sense. And we have AA, and we're going to do it 5, 5. What is 5? That's a 4 and a 1. So that's going to be, that's a fun number. 4 is 0.25. 1 is a 16th. It goes down further. We get 36 out of that. And our last one is FF, and we gave it like the smallest 1, so it should come out 1. So we've created a fully pipeline color conversion, right, multiplication thing. All we need to do is then combine all 3 colors and output 3 colors. Well, let's generate 9 colors. Reality. Add them out. Try that. Like it wouldn't be. We do a lot of coefficients and values. Okay. Well, it's on the hour ish. I think we've pipelined it and got working on EDA Playground. I'll go polish it up and get the different colors and coefficients working, and then need to figure out a way to implement that. I think I want to do a Verilator design that allows you to throw real colors into it. So we'll see that. Tomorrow I'll look at doing the LightX development. The next thing is probably gonna be LightX development using the Steam Deck. It's been a really good FPGA dev tool so far. Be interesting. Okay, sorry for this boring video. Back to FPGA development, but just showing off the EDA tools and writing a test bench from scratch. Yeah, getting some Verilog refresher, which is good. So good night. Hopefully see